In this video, I'd like to take a look at Unit 7, where we're studying Chapter 8 on proportional reasoning. In particular, we're going to take a look at Part 1 of Sections 8.1 and 8.2, where we are comparing rates. The objective of this lesson is to help you understand how to represent something as a rate, how to interpret it, and then how to compare rates. And using all of this information, kind of piling it all together and trying to solve some problems that involve rates. There are a few vocabulary terms that you need to be watching for: ratio, rate, unit rate, and rate of change. So make sure that you take note of these and that you watch for them and be sure to write a definition as they come across in the video. So first of all, a ratio. Well, turns out you've seen lots of ratios before. Ratios are simply when we are comparing two numbers. And we can write them in three different ways. We can write them with a colon, A to B. We can write it as a fraction, A over B. And if we were to actually say it in words, we would say A to B. And what we're doing is we're comparing two things that are the same. So in something like this diagram, if I said the ratio of blue dots to red dots is, what we would do is count the blue dots and count the red dots, and we'd come up with an answer like 6 to 5. There are 6 blue dots and there are 5 red dots. So that's what we call a ratio. I'm comparing something that is the same. They're dots, but they're different colors. And I'm showing what the ratio is of blue to red. Now, that leads us to the next one, and that is, what is a rate? Because a rate is also the comparison of two things, but it is different because those two things or quantities are not the same. Now, that may sound more complicated than it actually is, so consider this one. If you saw some students jogging along and someone said the students jog at a rate of, we might say something like 8 kilometers an hour. Well, if you take a look at what you're doing there, you are comparing. So in the numerator, you have 8 kilometers, and in the denominator, you have 1 hour. And what you're doing is comparing the amount of time, the passing of distance, I should say, the amount of distance that changes over time, 8 kilometers an hour. So one of the things about rates and ratios is that they should always be expressed in the lowest terms. Now, a ratio is easy. If you wrote a ratio or a fraction like 6 over 10, we would want you to reduce it. 6 over 10 is the same thing as 3 over 5. Well, the same thing has to happen in rates. And it's a little bit different looking. However, you will probably notice that your intuition is strong on this one as well. Let's take a look at this simple example. If you were told that your pay is $60 for 8 hours of pay, and if I were to ask you, so what is your rate of pay? How much are you being paid? Most of you would just naturally know what to do. You'd start by saying, well, I'm making $60 and that's in 8 hours. So if I divide the 60 by 8, I will get $7.50, which means that my rate of pay is $7.50 an hour. And you have done exactly what you need to do with a rate. You have turned it into what we call a unit rate because you made the denominator a 1. You took the number that was there, that 8, and you divided it into the 60. And so you have something called a unit rate where the denominator is 1. Okay, so let's take a look at another example. And what we've been given is some information about buying turkeys. Turkeys at a local butcher, turkeys at a local supermarket. And you're supposed to figure out which store has the best price. So if we start with our information, we're going to want to pull out what we see there. So at the local butcher, we're going to pay $42.89 for 12 kilos. And at the local supermarket, you're going to pay $1.49 for 1 pound. Now, when we look at this one, we've got to decide, well, all right now they're not the same. One of them is the amount we pay for kilograms, and the other one is for pounds. So we need to decide, well, what am I going to use? I need to make them the same so that I can compare them. Well, since we're Canadian, it probably makes sense that we would say what we pay per kilogram. So I'm thinking in my head, all right, I'm going to make the top a dollar sign, and I'm going to make the bottom a kilogram. So if I look at my work, I can see on the left-hand side, I'm going to have to change my number into a unit rate. I'm going to need to take that 12 and divide it into 42.89 to find out what it is per kilo. In the supermarket one, I'm going to have to change the pound that's down there into kilograms. And this is when we use something called a unit of conversion. And that means we're going to take two numbers that are exactly the same. 2.2 pounds is equal to 1 kilogram. And I'm going to write them as a fraction, because when I write two things that are the same as a fraction, and when a number is the same in the numerator and the denominator of a fraction, it's really just a 1. So I can multiply anything by a 1 and never hurt it. So I'm going to take this guy and I'm going to multiply it. I'm going to put the pounds in the numerator so that these two things, this pound and this pound, will cancel out. And I will be left, when I'm done, because they're canceling, with amount of money per kilo. Notice that I took care of that unit rate on the side as well. And when I actually calculate the numbers over here, I get an answer of $3.23 per kilo. So what I've done is now everything is the amount of money per kilo, and I can compare them. It tells me that the supermarket has the best price. Now, whether or not you would actually buy the turkey from the supermarket or your local butcher will depend on all kinds of things. The only thing that we've asked you here is, what is the best price? Well, the best price is at the supermarket. The next question has to do with gas mileage, and we're supposed to figure out which vehicle is better for gas mileage. Now, we have a Japanese-made car and we have a Canadian-made car, and they give us some information about how far it will travel and how long it takes, like how much gas it uses up. Now, one thing you need to know, and this is a really important thing for you to store in your memory bank, when you are talking about gas mileage in the metric system, you must use liters on the top, and down on the bottom, you will have kilometers, but it must be 100 kilometers. So we need to take our numbers and force them into this rate as you see it up above. Okay, so all I've done to begin with is I pull out what I know. It's 48 liters for the Japanese vehicle, and it's 65 kilometers that it travels. So I've put the liters over the kilometers. And then for the Canadian model, I'm doing the same thing, liters over kilometers. Now, it's hard for me to actually compare these guys because they're so different. So what I probably want to do is turn them into unit rates. So I'm going to take the 645 and divide it into 48, and the 392 and divide it into 32.1. Now, the problem with that is, though, when I make that unit rate, it's going to be 1 kilometer down on the bottom, and I want it to be 100 kilometers. So along with actually dividing this guy into that one, what I need to do is multiply them by 100. And of course, if I multiply the denominator by 100, I've got to multiply the numerator by the 100 as well. So with this one, I'm going to actually go ahead and multiply these guys out, and that will give me some answers. I'll have 7.4 liters over 100 kilometers. And I will have 8.2 liters over 100 kilometers. And then I've got them in the very perfect format. I can see that the Japanese model is definitely going to be the better for better gas mileage. So the last term that I'd asked you to watch for was rate of change. Once again, you can notice that there's the word of rate. So we want to look at how fast or slow is something changing. Well, turns out that that's actually the term that we use for something that we call slope in linear functions. So when we talk about the slope of a line, we're talking about the rate of change, the constant rate of change in a line. So let's take a look at a question that involves this. What we have here is a graph that's made of, you can see, 4 different lines. You've got them from this section, from here to here, from here to here, the third one, and the fourth one. And what I want to do is figure out a story that would describe what's going on in this picture. Well, that's not so bad, but before I do that, I do need to figure out what the actual rate of change is that each one of these represents. So we're going to do it for each of the 4. Let's do the first one together, and then I'll ask you to try the other 3 by yourself. So look at the first section, and remember, slope is calculated by finding out how much the y values change, or the rise, divided by how much the x values change, or the run, rise over run. So what we can see, if we go from this dot to this dot, is that the y values change from a 2 to a 0. So it's a change of 2. whereas in the x values, it's a change of 30 and it's minutes. Now, of course, kilometers per minute makes no sense to me. So I'm going to need to use a unit of conversion to change this. I want to change it so that I don't have minutes down here, but that I have hours. So I'm going to use a unit of conversion that puts the minutes up here so that I can cancel out the minutes. I know that 60 minutes is the same thing as 1 hour. So when I take my numbers, my minutes are gone, and I actually multiply them out, what I find is that it's equal to 4 kilometers an hour. And essentially, what you're saying is that the rate of change for this section of your graph is 4 kilometers an hour. Now, I want you to pause the video and try to do the same thing for the sections, the second one, the third one, and the fourth one. See if you can calculate the slope for those and check your answers with the slides that come after this one. So when you take a look at it, you should have found that the second one is a rate of change of 0 kilometers an hour. In other words, they didn't do anything. This one is a rate of change of 9 kilometers an hour. And the last one is a rate of change of negative 60 kilometers an hour. If you have any trouble with that, make sure you come in and ask about it, because this is kind of going back to finding slopes. Now, the question, just to remind you, was describe a story, basically, that this might be demonstrating. So let's say that this represents the distance that Susan travels on a Saturday over time. So if we look at it and think about it, okay, Susan was going 4 kilometers an hour for a half an hour. She's probably walking for half an hour. And then for 10 minutes, she's at 0 kilometers an hour, so she's resting. And then in this next one, for a good 20 minutes, I guess it is, she's moving at 9 kilometers an hour, so she's really running hard. And then for the last 5 minutes, she's going back to where she started, that's the negative, and she's going 60 kilometers an hour, so she's probably in a bus or a car. She's moving in something that can move her back to where she started at 60 kilometers an hour. Okay. Now, let's take some of the things we've learned then. We've talked about ratios, comparison of two things that are the same, rates, comparison of two things that are different. We've talked about unit rates, where we take the denominator and make it be a 1. And then we've also talked about the rate of change, something that we see in a linear function. So how do we use these things in questions that pop up? Well, as we go into this, one of the things that I want to stress is what we're learning is not so much about what the answer is in the question, but how we get there. I want to take a look at what is the method that we use. And one of the first methods that we're going to spend a little bit of time on in these questions that follow is using what we call unit conversion or unit elimination. We need to be able to convert rates often in what we do. So let's take a look at the first one. A faucet leaks 1 milliliter per minute. So that's 1 milliliter divided by 1 minute. Now, how many liters are wasted in a week? So if you think about what you're doing, you're taking milliliters per minute and you're changing it into liters per week. So watch what we do. The first thing I did was I decided to get rid of the milliliters and change them into liters. I know that 1,000 milliliters is 1 liter. So you'll notice this crossed off and I had my liters. So that took care of the top part. Now I've got the liters done, but now I need to change the minutes into weeks. So the first thing I used was minutes to hours, because I know that 60 minutes is an hour, and I cross off the minutes. And then I change the hours, and I know that 24 hours is 1 day. And then I change the day into weeks, and I know that 7 days is equal to 1 week. And so I get rid of the days. So if you take a look at the units that are left, you have liters and you have weeks. And when you take all those numbers on the top and multiply them together and divide them by the numbers on the bottom, you get an answer of 10.08 liters per week. Now that's all fine. When we have questions that involve measurements or things that we're used to, time or the length of something, that's easy to do. But how do you use these units of conversion when you're talking about something that feels more like a scenario or a word problem? So it says Paul is asked to order snacks for an office meeting of 180 people. She decides to order dessert squares, which come in boxes of 24. She estimates that she will need 2.5 squares per person. So the question is, how many boxes should she buy? Now, essentially, what you're being asked to do is to take 180 people and turn it or convert it into boxes of squares. So let's see how we might do that. We're taking people, converting them into boxes. So, first of all, what I know is that those 180 people will probably eat 2.5 squares a person. And you'll see the way I've organized it so that the people cross out the people. And so I end up with squares. Now, I don't want to know how many squares I have. I want to know how many boxes. So if I line that one up, I'm going to line it up so that the squares are canceling one another out and I'm left with a box. And that gives me the position of my numbers. I'm going to take 180 times 2.5, and then I'm going to divide it by the 24. And I get 18.75 boxes. Now, everybody knows we can't buy part of a box. So we write in our conclusion, she will need to buy about 19 boxes of squares. Now, if each person at the meeting actually only ate an average of 1.5 squares, how many boxes of squares will be left over? So let's see what we can do with this one. So we take 180 people and we multiply it by the squares per person, the box for squares. So we realize that we are only using 11.25 boxes, but remember that we bought 19 boxes. So when we find the difference of those two, we would say that there will be about 7.75 boxes left over. So one thing about this that you have to make sure of when you're doing these questions is always make sure that your units are common so that you can actually work with things and that they are something that you can compare. And when you compare them, consider turning things into unit rates of some kind. And that's a good starting point to be able to compare things. So the last question we're going to do in this video is the following. Now, this one is where Jeff lives in a town near the Canadian-US border. The gas tank of his truck holds about 90 liters, and he can either buy gas in his town, and it gives us the price per liter, or he can travel across the border into the United States to fill up, and it gives us the US dollars per gallon. So which option makes the most sense? Well, clearly we're going to try to compare these two things. We need to think about what do we need to change. Well, first of all, Canadian money, American money. We need to know what the conversion rate is. And then liters, metric liters to American gallons, how do I convert that? So the question in something like this would have to give you those conversions, and you can see them up here. I've listed them for you. We would definitely give this to you. We wouldn't expect you to memorize it. So let's take a look at the Canadian, which was $1.06 per liter, and the American, which is $2.86 per gallon. Now I'm going to be the Canadian, and I'm going to change the American one. So first of all, I'm going to get rid of the US dollars. So I put it on the bottom, so I cancel it out and use the Canadian on top. And then I want to get rid of the gallons, so I put the gallon on top and the liters on the bottom. The numbers are now in the correct position, so I can move things out. And what I find is that it's 98 cents a liter. So if you were to compare this one with this one, you can see right away that it makes more sense to buy the gas, at least in terms of its price, in the United States. You'll notice that the next thing I did was I figured out how much money he would actually save because he's got a tank of gas that's 90 liters. So I took that and multiplied it by 90 for both of them. And then I compared the amounts and I realized that it's actually $7.11 cheaper for him to fill his tank with gas in the States. So there you have it. We were comparing two things, had to change a couple of things to be able to actually say which one was best. So what we've done in this part one of this section is we've learned what rates are. How do we represent things that are information and rates? How do we interpret them? And how do we compare them? And then we've done some solving of problems using rates. Now the homework that you're going to need to do is from section 8.1. That's on page 458. Make sure you try these questions, check the solutions, and if you have any problems at all, make sure you ask for help.